Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So now we will discuss about reversible work and also irreversibility. So we will learn why we need to study or why we need to know about reversible work and also irreversibility. Okay, why do we need to understand about reversible work and also irreversibility, especially when we discuss or analyze actual engineering system, such as a gas power plant system as shown in the figure. Okay, so there are three reasons. First, for the actual engineering system, the dead state is hard to be achieved. So this statement, the term for dead state, actually we already mentioned in the definition of Exergy. So this dead state actually for the actual condition is very hard to be achieved, because most of the point in the, for example, in the gas power plant, the condition is not equal to the environment condition. Okay, the second reason, the analysis that involves the actual engineering system is not only for two fixed states, as we discussed in part number 1. Most of the example we discuss about a process that consists of only two fixed states, initial states and also final state. However, in actual engineering system, for example, a gas turbine engine, and this schematic diagram shows the actual gas turbine engine schematic diagram. So where we have compressor chamber, and so turbine. So in this schematic diagram, at least we need to analyze 4 different states: state number 1, state number 2, state number 3, and also state number 4. Okay, so the analysis will be slightly difficult when involved in the actual engineering system. Okay, the third reason is the process is not isentropic process, which means the process is not ideal. The process will involve heat losses, friction, and so on. And the isentropic process normally is limited to the adiabatic process. So the adiabatic process means the component or the system we consider no heat loss to surrounding through the wall of the component of the system. Okay, so if we describe the gas turbine engine cycle by using TS diagram, so the slide shows this TS diagram shows the process of gas turbine engine cycle. So in this TS diagram, we can see that we have the compression process in a compressor, and also the expansion process in a turbine. So for both processes, we have two types of process. For example, for the compressor, we have ideal compression process, and the process starts from state number 1 to state 2s. However, for the actual process, when we introduce, or when we consider heat losses, friction, and so on, so the process will be the actual process, where the process will start from state number 1 to state 2s. So this actual process, for example, for the compression process, the process is not isentropic, the process is not ideal. Okay, so for this case, we will not have the maximum potential. We cannot get the highest amount of work output produced from the system. Okay, because we already consider heat losses, friction, and so on. We only can obtain the highest work output if we consider the process is ideal, without any losses, without friction, and so on, which means the process we consider as isentropic process. Okay, so these are the reason that why we need to know about the reversible work and also irreversibility. So there are two quantities related to the actual initial and also final states. First, we have reversible work, W reversible, and also irreversibility, where we use the symbol of I. And other name for irreversibility is Exergy destruction. Okay, later on we will go into detail about reversible work and also irreversibility. Okay, before we refine the definition for the reversible work and also irreversibility, let me look a few terms that we need to know in terms of to understand the reversible work definition, also irreversibility. So the terms are the useful works and also the surrounding works. So for surrounding works, let's say we take two different states. State number 1, which is the system consists of a cylinder piston device, where we have a certain substance inside the cylinder with volume V1, and also we have atmospheric air P0 that gives force to the piston, and the direction of the force that produced by atmospheric air is in downward direction. And for state number 2, we have the same system, cylinder piston device. However, for state number 2, the volume of the substance is higher, which is equal to V2. Okay, if we consider expansion process, where the process will involve the increase of volume from V1 to V2. So due to the expansion process, the substance inside the cylinder will push the piston upward, and the direction of the force that produced by the substance inside the cylinder will be contradict with the direction of force that produced by atmospheric air P0. So in terms of expansion process, in terms of equation, if we analyze by using first law of thermodynamics, so we will get WU equal to WB minus W surrounding, where WU represent the useful work. So we can say that this useful work as the W net for the system. WB stand for the boundary work, the work that produced due to the moving boundary. Okay, so the figure shows the boundary of the system for state number 1 and also state number 2. And W sur is equal to surrounding work, the work that that due to the force that produced by the atmospheric air. Okay, that we call surrounding work. Okay, so if we expand what I call the equation for W surrounding, so we'll get a new equation where WU useful work equal to boundary work minus P0 atmospheric air multiplied by V2 minus V1 volume difference during the process. Okay, so this is the equation for expansion process for that involves surrounding work. And then for the next process, let's say we consider the compression process from state 2 to state 1, where we have the decrease of volume from V2 to V1. Okay, now due to the compression process, the piston must move downward so that the volume of the substance inside the cylinder can be decreased. So if you look at the direction of the force that exerts to the piston with the direction of the force that produced by atmospheric air P0, so the direction is parallel with each other. So in terms of compression equation, in terms of energy, so we will have useful work WU equal to WB boundary work plus W surrounding or surrounding work. So Now we have plus symbol because the direction of force for the compression and also the direction of force that due to the atmospheric air is parallel. Okay, so the direction are parallel. So now we have, instead of negative for the expansion process, so for compression process we have positive symbol, where WU equal to WB plus P naught V2 minus V1. And these two equation for expansion also compression process are only valid for moving boundary system. So the system that we have the movement of the boundary as shown in state number 1 and also state number 2, where we have cylinder piston device. So cylinder piston device is one of the example of the system that involves moving boundary. However, for the system without surrounding work or no surrounding work, such as cyclic device, steady flow devices such as compressor, turbine, pump and so on, and also rigid tank. So for this kind of devices or systems, the system or the devices will not involve any moving boundary. So because no moving boundary, there will be no volume change. So delta V will be equal to 0. Okay, so if you implement into equation for expansion and compression, the term for V2 minus V1 will be 0. So no effect by the atmospheric air to the system. So W surrounding will be 0. And at the end, the useful work will be equal to the work that produced or required by the system. Okay, so that is the difference between surrounding work system and also without surrounding work system. And now we can differentiate about, we can know what the meaning of useful works and also surrounding works. Okay, now we will look about the definition for reversible work and also irreversibility. So for reversible work, W reversible, the definition is reversible work equal to the maximum amount of useful work that can be produced as a system undergoes a process between specified initial and final states. So if you look at the definition of the reversible work, the definition quite similar with the definition of Exergy. Okay, so for reversible process, in order to obtain reversible work, the process must be reversible, where the initial state can be changed into final state, and then the final state can be changed into initial state again. Okay, so if the process is reversible, so we can produce W reversible or reversible work. W reversible will be equal to Exergy when the final state equal to the dead state, where the final state of the process equal to the environment condition. So we can call W reversible or reversible work equal to Exergy. The value of reversible work will become same as the value of Exergy, the maximum potential of a system. Okay. However, for the irreversibility I, or Exergy destruction or Exergy destroy, definition for the irreversibility is the difference between reversible work, W reversible, and also the useful work, WU, where irreversibility I also equal to Exergy destroyed. So when the question asks you about Exergy destroyed, actually you need to calculate the value of I, or irreversibility. Okay, in terms of formula, we have two formula for irreversibility. First, for work producing device such as turbine, because turbine will produce work. So the irreversibility formula, I equal to W reversible out minus W useful out. Okay, so I equal to W reversible out, or we can say that W for the ideal case, the maximum one, minus W U out, which is normally represent the actual W out. And for work consuming device such as pump and also compressor, I equal to W useful in minus W reversible in. So this equation also similar as I equal to WU in, which is the actual amount of work in that need to supply to the device, minus W reversible in, which is normally represent the ideal W in that we need to supply to the work consuming device such as pump and also compressor. Okay, so the irreversibility actually represent the waste work potential or the lost opportunity to do works. Okay, suppose if we can minimize the value of I, we can increase the amount of work produced by certain system. Okay, so if we have greater value of I, that means the system is not good, because most of the energy wasted to surrounding. Okay, so if the condition of I equal to 0, so when I equal to 0, this means that the process of the system or the device is ideal. Okay, so now, because if we look at the equation for irreversibility, when I equal to 0, then we can conclude that W reversible or reversible work will be equal to WU useful work, because the irreversibility value is 0. Okay, so for this condition, actually when I equal to 0, we ignore irreversibility factors such as heat losses, friction and so on. That's why we have the value for I equal to 0. Okay, so let's say we have this schematic diagram shows the schematic diagram for simple steam power plant, and the second figure shows the thermodynamic cycle to describe the process for the steam power plant by using TS diagram. There are two types of cycle here. So the red cycle represent the ideal cycle, and the cycle with dash black line represent the actual cycle. So if we look at the process for state number 1 prime to state number 2 prime, which is represent the ideal process for the pump, the process is isentropic. So because we ignore irreversibility, no losses, no friction and no heat losses and so on, that's why the value of I equal to 0. Okay, similarly with the process for the ideal process for the expansion process in the turbine. So for the process from state number 3 prime to 4 prime, the value of I equal to 0 because the process is ideal. So we ignore heat losses, we ignore friction during the process. However, if we consider the actual process for the expansion, so we will get that the value of I is not 0. WU will be lower than W reversible. And for the pump, for the actual process, we will get WU useful work will be greater than W reversible. Okay, so that's how we can use or we can describe the reversible work and also irreversibility for certain process. Example 1.3, a heat engine receives heat from a source at 1200 Kelvin at a rate of 500 kJ per second and rejects the waste heat to a medium at 300 Kelvin. So the power output of the heat engine is 180 kilowatt. determine the reversible power and also the irreversibility rate for this for this process. So now the question asks you to determine to determine the reversible power and also irreversibility. So this term actually for reversible power refer to W reversible dot, and irreversibility rate refer to I dot. So so we need to divide W reversible and also I formula with time. In terms of solution, so first we draw the simple schematic diagram. So we have heat engine, we have energy source at temperature 1200 Kelvin, and the engine will receive heat Q in dot equal to 500 kJ per second, and the heat or energy released to sink at 300 Kelvin. And because this is a heat engine, this heat engine will produce W out. So we have W dot out equal to 180 kilowatt. Okay, now we know that the equation for thermal efficiency for reversible process is mu TH reversible equal to 1 minus TL over TH. TL stands for low temperature, TH stands for high temperature. So if we relate the temperature with the problem, example 1.3, so TL actually equal to T sink, TH equal to T source. So for this equation, remember, you need to remember that the temperature must be in Kelvin. So substitute the data that we have into this equation. So we will get thermal efficiency for reversible process equal to 0.75. So the maximum efficiency that we can obtain from this system or from this process is 75%. Okay, now we have second equation for thermal efficiency for reversible process, where mu TH reversible equal to W dot reversible divided by Q in dot. So if we rearrange the equation, so we will get the equation for reversible power, which represented by W reversible dot, and this term also equal to W reversible dot out, because for heat engine the system will produce W out. So W reversible dot or W reversible dot out equal to mu TH reversible multiplied by Q in dot. So substitute all the data obtained or all the data that we have. So the value for W reversible out dot equal to 375 kilowatt. So the maximum power output that can be achieved by this heat engine is 375 kilowatt. Okay, so in order to determine, just now we already obtained the reversible power, W reversible dot or W reversible out dot, which is equal to 375 kilowatt. And next we need to determine the irreversibility rate, where for work producing device we can use the specific irreversibility formula that we have learned, where I dot equal to W reversible out dot minus WU out dot, where here we know that W useful out dot actually refer to the power output for the actual process, and the value already given in the question, which is equal to 180 kilowatt. So substitute the value or the value that we have, so we can obtain the rate of irreversibility that obtained for this process equal to 185 kilowatt. Okay, I dot irreversibility rate equal to 195 kilowatt. So this value shows that the system will lose or waste the system will waste the amount of energy equal to 195 kilojoule per second for every second. In total, the system will lose power 195 kilowatt for the whole system. So in order to improve the system, we need to reduce the amount of I dot. So if we can reduce the amount of the value of I dot lower than 195 kilowatt. So we able to increase the efficiency of this heat engine.